Alright, welcome. This is Newton's Laws application. So what I'm going to solve right now is a type of problem where you have, you have a rope attached to a box of books. They pull with a certain force at a certain angle. They give you a coefficient of friction, so find the acceleration. Okay, so first thing I'm going to do is always draw a free body diagram if it's not there already, so FBD. So here we go. Here is our free body diagram. We know gravity will be acting on the block. I know friction is going to act against the object. I always assume the objects go to the right, so with that said, I'll put friction this way. Then it says the student pulls the rope at an angle, so here's the horizontal, so here's the rope. That's 30 degrees, like that. And then I'm going to draw the force normal. Now the force normal should be less than the gravity, so let me just make that change. The reason why is because, remember, the force due to, the force due to gravity is pulling this down. That's our downward force. But notice that this applied force actually makes we have an X. And notice that's pulling up, which means the ground is not pushing down as much, which is why this is less than this. Because we're pulling this up slightly, leaving, like I said, the ground having a less push on the ground. So force normal is less than force gravity, main thing because of this. Alright, so there's our free body diagram. So the next step, what I'm going to do is to find my F forces in the X and F, my forces in the Y. So using kind of the same method, let's say we have one force in the X, which is the force friction, and we have the FAX here. Those are all my X forces, which leaves all of my Y forces in the yellow. This one, normal, and that. Notice I didn't highlight that one because, again, Newton's laws only work in one direction, so we gotta make sure that if it is at an angle, we take the directional pieces or the components of the forces. So now after we find those, we're going to make the equations for the sum of the forces in each direction, F, and the sum of the forces in X and Y, And then we either set it equal to 0 if no motion, basically, in direction. So basically our Y value is going to be set to 0 because we're not moving up or down or accelerating anyway. And then we'll set it to MA if acceleration mentioned. So as you notice, we do have an acceleration. So we're not going to set it to 0 in this case. We're going to set it equal to MA. So let's make our equations. So I do the sum of the forces in the X. Now I put an arrow here because what I'm doing here is making the equation. It's not setting this equal to the sum of the forces FAX. So I'll even write it below. So with that said, that means that I'm going to write the following expression. The force applied in the X is positive. I'm going to assume right positive minus force friction because we're going backwards. It's going to be equal to MA. Now I'm going to put the X here just to specify that we are accelerating in this direction. And if you think about what someone's doing, they're pulling books. They're going to be moving horizontally. They're not going to be moving vertically at all. So that's the sum of the forces in the X. So sum of the forces in the Y will be as follows. We have force normals up minus the force of gravity plus the force applied in the Y. Now this becomes a plus because we're up right here. Now since it's not moving up or down, we set this one equal to 0 like that. So now that I have this, then I kind of notice that I look back at the question. Find the acceleration. So I need to find this. That's what I'm looking for. I don't have this. I do have the value of this force, that's 90 newtons in the angle, but we need to find this. Now recall, force friction is equal to force normal times mu. So, with that said, force normal times mu, I need to find the normal force, and we do have mu. This is the mu value, because then we can plug this in to solve for A. So we got to solve this first. So with that said, if I move everything to the opposite side, we have an expression for force normal. Sorry. So we have force gravity. We add that over and subtract this over. Oops, just like that. Perfect. And now we have an expression for our situation, and we have both of these terms. So let me write this out explicitly and then let me solve. So remember, Fg is mg, so we have the mass, which is right here. G is just our constant, and then we have our hypotenuse of our triangle, or in other words, the we have the force applied right here. So remember, that's force times, for the y piece, is going to be force times sine of the angle. So force times sine angle, force applied like that. So force normal is going to equal to, so I'll just make an arrow right here, the 20 kilograms times 9.81 minus the force applied, 90, times sine 30. So let's do that out. So when I do, I get 151.2 newtons, and that's the force normal right here. So I'm finding just writing what I'm doing. I'm finding force normal to find force friction. Here we go. Step 5. Find now that we have friction, we can find the acceleration using the sum of the forces in the x. So I'm just going to rewrite what we have already. Minus force friction equals ma. So this is going to be force times cosine of our angle. So I'm looking over here. So minus force friction, which is going to be force normal times mu equals ma. And then what we have is 90 times cosine of the angle minus force friction. Oops, I might as well write the angle. Cos of 30 minus, we have 151.2 newtons, that's force normal, times mu, which is 0.5. I got that from the problem right here, equals the mass times acceleration. So now I'm going to find acceleration by plugging in my values. 90 times cosine 30. Then I'm just going to do 151.2 times 0.5. So just so I can have some numbers so you can follow along here. So what I have so far is this becomes 77.94 minus 75.6 equals 20a. So now I'm going to do that algebra. My acceleration becomes 0.117 meters per second squared. And there you have it. That's our acceleration for our box of books that this person is pulling down the sidewalk. Okay, that will be it for this problem.